In this video, we're going to talk a little bit about how charges end up moving around a circuit. So what we're going to do is go back to our picture of a mechanical battery. So here in the mechanical battery, we have a positive plate and a negative plate. And between those two things, we have this conveyor belt that brings up negative charges and ends up putting them over here on the right plate to allow the charges to move around our circuit. So if we were going to draw the direction that the charges move, they would go from the negative plate to the positive plate and back again. So the question is how does this happen, right? So you're used to sort of thinking about a battery and having some current driven around the circuit. And if we follow the electrons, they're going to go around the circuit like this. But how can we actually model that behavior? How does it happen? And we have to go back to thinking about, well, what is the force that these charges would experience? The force that those charges are going to experience is an electric force. It's one due to the electric field. And so we have to be able to identify the specifics of the electric field to say how these charges are moving about around this circuit. So what we're going to do is get rid of this for a moment and redraw it. And we're going to analyze what happens when we consider different pieces of the electric field that could contribute to this. So we'll redraw our positive plate and draw our mechanical battery and our negative plate. And we'll redraw the circuit as it goes around here like this. And so the first thing that we'll consider is, what if this was due to the electric field of the battery? Well, the first thing that we have to pay attention to is the fact that when we hook up a battery into a circuit, we're going to have a constant current. This is a so-called steady state current. It's basically that we expect the current that's driven through the circuit to not change as we go around the different parts of the circuit. And that's a really big piece of what's going on. The other thing is that we would expect that the direction of the current to sort of follow the path of the circuit, if you will, basically how the circuit is actually laid out. So those two observations we expect to be able to reproduce with this picture. So if we look at the battery itself, on this side of it, the electric field is going to point towards the negative plate. That seems okay, right? Because roughly what will happen is there's going to be a force that kind of points backwards, which would drive charges away from the negative plate. That makes sense. On this side, this electric field is going to point also to the left. That's also not so bad because the force that we would expect is going to actually point towards the positive plate. And so at least near this region, the pushing that we're going to see on those electrons follows what we would expect, away from the negative plate and towards the positive plate. In this region over here, let's say down here between the two, where we see a fringe field, the field that is due to these two plates but is kind of far away, we would expect the electric field to point in this direction. But here it's going to be smaller than near the battery. And so the direction seems like it makes sense. It's fine. There's going to be a push on those charges sort of in the direction we would expect them to go. And if we followed the field sort of all the way around, it kind of looks like it would work okay. So in terms of the direction, we're probably okay, sort of. But the issue is that that electric field is going to be smaller as we get farther away from the plates. And that is potentially quite problematic because then we might not get a constant current because that electric field, the pushing that we're going to see on those charges, that constant force that's necessary to drive them through the circuit, is going to be different depending on where we are in the circuit. And so we would not necessarily expect a constant current. That's problematic for the analysis that we're doing here because we expect this current to be constant. So where might this electric field stem from? What could we possibly posit that would allow us to do this? Well, it turns out that there might have to be something going on inside the wires. And the way to convince yourself of that is not necessarily just this idea that it's smaller, but imagine if you had a piece of wire that was connected to a battery that was very, very long, or that you oriented in different ways. What we observe is that the current that we measure is still the same, regardless of the sort of orientation of that wire, even though the electric field near that wire could be potentially different. And so there must be something about the wires that produces an electric field that we have, that we're able to sort of model as having a constant field throughout the circuit. So one way to do that is to say, well, if the charges move around this way, we expect an electric field, a constant electric field, to be produced everywhere in the wires to point from the positive charge, positive plate to the negative plate. That is, there's this electric field that's constant in magnitude everywhere throughout the wire. So to construct that, what we have to do is build a model of what kind of charges would produce such an electric field. And a pretty reasonable one is what we will refer to as a surface charge gradient. So you can think about it this way. If I were to have a piece of the wire like this, and there was a bunch of positive charges over on this end of the wire, and a bunch of negative charges over on this end of the wire, I would produce an electric field that kind of points to the right like this. Now, in going from this large positive to this large negative, we'll have to go through sort of zero net charge. And it turns out that that's exactly what happens, is we end up with sort of a distribution of surface charge along the wire that looks like this. It is a gradient in the sense that it changes sort of this at this constant rate across the surface here, and it continues to produce an electric field that points in one direction with a constant magnitude. Now we can take this picture and we can sort of wrap it around what we have going on up here and reproduce this figure to make sense of what that surface charge gradient is and how it produces this electric field. So if we draw a similar sort of picture here, there's a lot of positive charges here, there's a few positive charges here, there's a couple here. We go through zero, there's some minus charges here, and then a bunch near the plate. This kind of ring of charges, this surface charge gradient that we're seeing here, will produce this kind of electric field that we would expect to see, one that is constant in magnitude and sort of follows the direction that the wire is laid out. So in the case of A and B here, that is that we have a constant current. Well, if we have a constant electric field, we will have that, and that the direction will follow the wire by drawing this sort of picture here where we show what it looks like in a straight line situation and then curve it around. We could imagine that these charges will readjust appropriately so that we get this electric field that follows the wire and thus produces a constant current, that is a constant sort of rate of electrons going from this side to that side. So these surface charges, they seem like they're a construct. They seem like they're something that we're using to sort of get out of trouble here. But really, when you have a very, very high voltage circuit, you can actually show that on one side of the circuit, there are positive charges on the surface, and on the other side of the circuit, there are negative charges. And there's a video in the notes to show you that you can actually do this when you have a high voltage line.